All right, we want to analyze angular momentum and its relation with the moments of forces around, let's say, some point C, which is not necessarily center of mass or center of gravity on Earth, G. So let's say center of mass is G, and we want to analyze the linear momentum around point C. So let's say we have, our rigid body can be thought of as a lot of point masses glued together, right? So we can think about a lot of point masses glued together and makes a rigid body. So let's just pick two of such points, call them I and J, but for now, let's analyze just I. So we call this Ri. And let's say it has relative velocity if we attach a coordinate system at C. If we have a coordinate system at C, let's say this has the velocity of vi with respect to C. So we want to see sigma of, we define our H around C as sigma of Ri cross product, meaning moment of Mi VIC. So we look at the relative velocity of them. So the velocity, in fact, the velocity of A, the velocity of I is the velocity of C plus that relative velocity. So we want to take this velocity of C out of the picture because we want to calculate angular momentum around that C if we have a coordinate system there. So we want to take out that velocity of C outside. So as if, for example, we want to see what is this we want to see the same thing for this type of motion and this type of motion, that point C is also moving. So we want to look at that angular momentum irrespective of the velocity of that C. That's why we put it like VI relative to C. So now, if we do the derivative of this, let's see, this is a vector. You can put a vector sign or just make it with bold letters. So this would be sigma. This is summation over I, by the way. It is all those point masses that makes the rigid body. So it would be derivative of this cross this plus this cross derivative of that. Remember, for dot product, for example, if we wanted to do the derivative, it would be f prime dot g plus f dot g prime. Remember product rule? The same thing happens for cross product. If you expand the cross product, you would see it is the same thing. So it would be derivative of this cross this. And derivative of this, it is omega cross Ri. There is another video that explained that, but for now, think about it this way. Ri, that's the magnitude of Ri is not changing because it is a rigid body, but the direction is changing, right? Because it might change, the whole thing might rotate. So how much it would change? Omega cross Ri. Because we want to see how much Ri is changing with respect to our inertial coordinate system. So in that coordinate system, because this system is rotating, the change of that is omega cross Ri, which is in fact VIC. If you VI with respect to C, this is in fact omega cross Ri. So in fact, we would have this cross itself and some Ri. You see, we have that, some Mi. Because again, that relative velocity is in fact, because we can write it, I mean, VR, I can say R, capital R, I equals to RC, capital R of C plus Ri. I'm saying that if I have an inertial coordinate system and I call this Ri, RC, and I call this Ri, then I can write Ri equals to RC plus this. This is just addition of two vectors. Then from this, doing derivative of this, I get VI, absolute velocity of V, equals to absolute velocity of C plus that thing, relative velocity, which becomes that equation. And that relative velocity is in fact omega cross Ri. All right, so let's erase it now because we don't need it. If we know what we are doing. So far we have done the derivative of this one plus derivative of this term. Rather than VIC, I can write it VI minus VC, right? So I'm saying that I can write VI with respect to C, I can write it as just took that to the other side, right? So I can write this VIC as VI minus VC. This is what I want to do the derivative of. So I keep that. So I'm doing this MI constant derivative of this, which is derivative of this minus derivative of that. So this would be AI minus derivative of VC is AC. Because these are absolute values. I mean, I don't need to worry about that, those omega business. This is with respect to that inertial coordinate system, both of them. So this term is zero because I have something cross itself. And by the way, this mi is a scalar. I can take it out. So for example, you see, if I have vector A cross 5 vector B, I can write it as this 5 can comes out and I can write it at A cross B. If you expand this and this, you will see that this 5, this scalar can come out. Don't forget that for cross product, we can't interchange them. It is not easy to work them. It is not commutative. I mean, I can't write it that way. If I have something like that, I can't write it as A cross B cross C. It is not true for cross product, but numbers, usually they can move around. And I mean, in this case, this MI is just a number. So I have this cross itself, and any vector cross itself becomes zero. Remember, cross product is, I mean, A cross B is the magnitude of that is magnitude of A, magnitude of B, and sine of the angle between them. So if I have A cross A, sine of angle between A and A is zero, so this becomes zero. So cross product, any vector with itself, it becomes zero. So this whole term disappears, and I'm left with HC equals to RI, and I write it MI, I can bring it that side, cross AC. I write the second term first, so that negative, plus I, RI, MIA. And this is due to the second law of Newton. This is sigma F, right? All the F's that are, let's say F1, F2, and I call this Fij, meaning that it is F on I from J, internal forces, because we might have two particles that have forces, apply forces on each other. But this is sigma F, all the Fs. I call this F total. Let's call it F total of I. All right. So this, now look at this term. MIRI, this AC is constant. I can bring this out of summation. So it would be MIRI cross AC. I can bring this out of summation because again, this is a constant. For example, if you have, these are side notes that I use. If you have, for example, let's say 5A1 sigma of 5AI, and I goes from 1 to, let's say, 5 or 3, then I would have this equals to 5A1 plus 5A2 plus 5A3. I can write it as factor out 5, and then it would be A1 plus A2 plus A3. And I can write it as sigma, right? Sigma I from 1 to 3 AI. So you see, this 5 constant number can come out of summation. The same thing here for AC. Now, MIRI, the summation of that, it would be over all the i's, it would be total M R of G with respect to C. This is the definition of a center of mass. Remember, center of mass, if I have 3 masses, for example, and I pick some coordinates, some origin for a coordinate, and let's say this is M1, M2, M3, the center of mass, the x coordinate of that, x of G, equals to M1, x1 plus M2, x2 plus M3, x3 over M1 plus M2 plus M3, right? And this is total mass of the system. So this is that M. You see, mxg equals m1, x1, m2, x2, m3, x3. The same thing for y. So we can say mr, I mean the coordinate of that. So this is what we are doing there. Nothing new. So this would be I, R, I, F, I, T. Now, about this, we can forget about internal forces. Why? Because think about these two particles. Due to the third law of Newton, if I have some force like that applying on I, so I would have the opposite of that applying on J, right? So if I add over all particles, for each Fij, I would have, and let me erase this part and I use this side as a side note. So I would have Ri, for example, cross Fij, right? I'm talking about just this force between these two particles. And I add them because I sum over all particles. Somewhere in the summation, I would have this as well. Cross negative Fij, right? And this negative can come out, so it becomes Ri cross Fij minus Rj cross Fij, and I factor out Fij. So I would have Ri minus Rj cross Fij. And this Ri minus Rj, it would be the vector connecting these two. So the vector connecting these two is parallel to Fij, right? It's along that line, and cross product, remember that sine of angle between them, it would be 0, right? You might ask here that what happens to the electromagnetic forces, for example, that we have Fij that way. Then again, still it was proven experimentally that it would be 0, but think about just mechanical system for now, and the forces are along that line. So it would be 0 because this Rij, this is in fact Rij, the vector that connecting these two, and cross product of that would be 0. So we can think that, okay, forget about all the internal forces, just put the external forces. And this is moments of forces, right? Let's call this M of all forces. I forgot to put that negative sign here. And I have this equals to negative M R G C cross AC. So now I have all the moments, let's say sigma of moments, all the moments equals to H dot of C plus M or G with respect to C cross AC. So this is that law that we were looking for. The change, I mean, the moments equals to change in the angular momentum around point C plus that term. Now, if this is center of mass, if C, look at this, look at this term. There are 3 ways that this can be 0, right? There are 3 ways that RGC cross AC is 0, right? Let's erase this. One of them is this RGC is 0, right? This means that C is G, because if C is the same as G, the vector that goes from C to G is 0, right? So we can write this for the center of mass. So we can write sigma m equals to the rate of change of angular momentum around center of mass. The other condition is that AC is 0, right? This means that C is a stationary point. For example, if you have something like rotation around a fixed point, then CAC is always 0. This is another condition. So we can write this equation for around a stationary point. That's why there are a lot of problems that you can use the same equation when we have rotation around that. We can write moments around that point and it equals to the rate of change of angular momentum. The other condition that is rarely used, you can safely forget about that, is that this cross that is equals to 0, meaning that these two are parallel. So RGC is parallel to AC. Then if it is parallel, the sine of angle between them becomes 0. So acceleration of C is parallel to the RGC, meaning that, for example, if I have this RGC, you see, this is R of G with respect to the point C. The acceleration of point C is along that line. So this is the third case, which is rarely used. So you can safely assume that these are the only 2 cases, all right, that we can use it. safely use it. Now that we have this equation, let's get back again and see how we calculate that I for 2D and 3D.